The twin paradox. Who's really older? Imagine two identical twins, Alice and Bob. Alice stays on Earth, living an ordinary life. Bob, on the other hand, boards a spacecraft and heads off to a star system 10 light years away, traveling at 99.9% the speed of light. He flies there, turns around, and returns to Earth. From Bob's point of view, the journey is short, a few years, maybe even less. But when he returns, Alice has aged decades. She's old, wrinkled, maybe even retired. And Bob, he looks almost the same as the day he left. It sounds like science fiction, but it's not. It's Einstein's theory of relativity in action, and it gives us one of the most famous thought experiments in physics, the twin paradox. Here's where the confusion begins. In special relativity, motion is relative. If Bob is moving away from Alice, then Alice is also moving away from Bob. So why should time slow down for Bob? Why not for Alice? Shouldn't each twin see the other aging more slowly? That would be true if both remained in constant straight-line motion. But that's not what happens here. Bob turns around halfway through. He slows down, reverses direction, and speeds up again. That moment breaks the symmetry. Alice never changes her motion, but Bob does. And in relativity, that change matters. This change introduces acceleration, something Alice never experiences. And acceleration, even in special relativity, identifies who's really switching frames. Bob is the traveler. He leaves Earth, he turns around, and he comes back. He experiences a different path through space-time. Now here's the truly mind-bending part. In Einstein's universe, time is not a universal constant. It's more like a path you carve through the fabric of reality, and different paths through space-time lead to different amounts of time experienced. Bob's path, moving close to the speed of light, compresses time for him. He lives less, he sees less, because time for him literally ticks more slowly. This isn't just theory. In 1971, atomic clocks were flown around the world on commercial airplanes. When they returned, their time readings disagreed with clocks that had remained on the ground, exactly as relativity predicted. And today, GPS satellites have to adjust for these time differences constantly. If they didn't, your phone's location would drift by miles every day. So while it feels like a paradox, two twins living different lifespans from different perspectives, it's not a contradiction. It's a demonstration of how time, space, speed, and acceleration are all part of the same cosmic system. Time isn't ticking out there like some universal stopwatch. It's personal, it bends, it stretches. And sometimes, if you're fast enough, it nearly stands still. The twin paradox shows us that space travel at near-light speeds won't just take us far away. It might also take us far into the future. When we finally reach for the stars, we might leave our own time behind. And for the twin who stays, they'll be waiting a long, long time. The relativity of simultaneity. What happens now? What does now really mean? We use the word all the time. This moment, this instant, the present. But in the strange world of relativity, now isn't as simple as it seems. Imagine you're standing still, looking out at two lightning strikes hitting either end of a train track. You see both flashes at the same time, so you say, they happen simultaneously. To you, that's the undeniable truth. But what if you're sitting on the train, moving fast toward one end and away from the other? Suddenly, those two lightning strikes don't look simultaneous at all. You might see the flash at the front before the flash at the back, or vice versa. Your now is different. This isn't a trick or an optical illusion. It's the relativity of simultaneity. Two events that seem simultaneous to one observer may happen at different times for another, depending on their motion. Why does this happen? It's because information, like light from the lightning, takes time to travel. When you're moving, you're changing your perspective on when events happen. Space and time blend together into a single fabric called space-time. And moving through space affects your slice of time, your present. In fact, there's no universal now that everyone shares. The universe doesn't come with a cosmic clock ticking for all. Instead, every observer slices space-time differently, creating their own now that can't be directly compared to another's. This shatters the everyday assumption that time ticks the same everywhere. It means your present moment, what's happening right now for you, could be someone else's past or future. Events you see as simultaneous could be spread out over time from another's viewpoint. And this has deep consequences. It's why the order of distant events can change depending on who's watching, as long as those events don't influence each other causally, so cause and effect remain intact. So when you think about now, remember, time isn't a universal river flowing the same for everyone. It's more like a patchwork quilt, stitched together differently depending on how fast you're moving and where you are. Relativity shows us that now is relative, and that changes everything we thought we knew about time. The ladder paradox, shrinking reality. Imagine a ladder that's 20 feet long, and now imagine a garage that's only 15 feet deep. Simple enough. The ladder doesn't fit. It sticks out the back, case closed, right? But what if the ladder is moving really fast, close to the speed of light? Now, from the point of view of someone standing next to the garage, something strange happens. The ladder shrinks. Not physically, but due to an effect from special relativity called length contraction. At high speeds, moving objects appear shorter in the direction of motion. So the 20-foot ladder, flying at near light speed, contracts, say, down to 14 feet. Suddenly, it fits. You could even imagine slamming the garage doors shut with the entire ladder inside. Problem solved? Not quite. From the ladder's point of view, it's the garage that's moving and shrinking. Now the garage is even smaller than before, maybe just 11 feet deep. So how can it possibly hold the full ladder? We've arrived at the ladder paradox, a collision between intuition and relativity. Two observers looking at the same event come to opposite conclusions. One sees the ladder fit, the other sees it doesn't. Who's right? Here's the twist. They both are. The key lies not in the size of the objects, but in the timing of events. When the garage observer says the ladder fits, they're talking about a moment in their own frame when the entire ladder is inside at the same time. But for the ladder's perspective, the garage doors don't close simultaneously. The back door shuts before the front of the ladder arrives, and the front door opens before the ladder hits it. So from the ladder's point of view, it never fits inside completely at any one moment, but it also never hits the walls, because the doors open and close at just the right times. No contradiction, just different slices of reality. This is the strange harmony of special relativity. Space shrinks, time stretches, events rearrange themselves depending on how you move. The laws of physics stay consistent, but our experience of them changes. So the next time something seems impossible, like fitting a ladder into a garage that's too small, remember, at near light speed, space itself becomes flexible, reality bends, and what's true for one observer might be completely upside down for another. But in Einstein's world, they're both telling the truth. Velocity addition, why light is always light speed. Let's say you're driving a car, fast, 60 miles per hour. A ball rolls across the dashboard at 10 miles per hour in the same direction. To someone standing still on the sidewalk, that ball appears to move at 70 miles per hour. That's how we intuitively understand motion. Speeds just add up. But what if instead of a ball, you turn on a flashlight? From your perspective, light moves away from you at 299,792 kilometers per second, the speed of light. But here's the shocker. From the sidewalk, it's going just as fast, exactly the same speed. No matter how fast you're moving, how fast you're chasing it, or how fast you're fleeing from it, light always moves at the same speed. Always. That's not a glitch in the math. It's one of the fundamental principles of Einstein's special relativity. And it leads us to something that breaks every intuition we've ever built about motion. The relativistic velocity addition formula. In our everyday world, if you're moving at speed A and something else is moving at speed B, you just add them together. Easy. But near the speed of light, addition works differently. Imagine this. A spaceship flies past Earth at 90% the speed of light. From inside, it launches a probe forward at 50% the speed of light. You might think, okay, from Earth's perspective, the probe is going at 140% the speed of light. But the universe says, nope, nothing, not even combined velocities, can exceed the speed of light. Instead, the velocities combine using a special formula that ensures the result is still less than light speed. Always. That's built into the structure of space-time itself. Because if light didn't always travel at the same speed, none of Einstein's theory would hold. GPS wouldn't work. Lasers wouldn't be predictable. Causality, the idea that causes come before effects, could fall apart. And worst of all, different observers could disagree not just on when something happened, but whether it happened at all. But because the speed of light is absolute, we get something amazing, a universe that flexes to preserve this limit. That's why time dilates. That's why lengths contract. That's why simultaneity breaks down. It's all to make room for one cosmic rule. Light always moves at light speed, no matter what. So the next time you shine a flashlight from a speeding car, remember this. You're not adding to light's speed. You're witnessing a cosmic constant, something so deeply baked into the universe that space and time themselves bend to protect it. Light doesn't follow our rules, we follow its. Mass-energy equivalence, why you can't hit light speed. What if you had the fastest spaceship ever built, engines roaring, fueled by the power of stars? Could you just keep accelerating, faster and faster, maybe even hit the speed of light? Short answer, no. Long answer, Einstein. It all goes back to one of the most famous equations in science, E equals mc squared. 3 symbols, endless consequences. At first glance, it tells us that mass and energy are interchangeable, that if you take a tiny bit of mass and unleash its energy, say in a nuclear reaction, you get a colossal explosion. But the equation doesn't just describe bombs, it describes motion, and it quietly hides a cosmic speed limit that nothing with mass can ever cross. Let's break it down. The faster you go, the more energy you need. That makes sense. Push a car, it moves. Push it harder, it moves faster. But near light speed, something strange happens. That energy doesn't just make you faster, it also makes you heavier. Not in the bathroom scale sense, but in the relativistic sense. As your speed increases, your effective mass increases too. You're dragging more and more inertia behind you. You're not just going fast, you're becoming harder to move, harder to accelerate. Every bit of energy you pump into the system adds more to your resistance than to your velocity. And as you approach the speed of light, that resistance skyrockets. To reach 99%, the speed of light takes a lot of energy. To reach 99.999% takes vastly more. And to hit 100%, that would require infinite energy, which no amount of fuel, technology, or clever engineering can ever provide. This is why photons, particles of light, are the only things that can travel at light speed. They have no rest mass, so they're not weighed down by energy demands. They don't accelerate to that speed. They're born there. Everything else, we're bound below the limit. This isn't just a technical detail. It's a fundamental rule of the universe. The same rule that powers stars, governs nuclear reactions, and gives matter its energy, also draws the line we can never cross. So when we say nothing can go faster than light, it's not because light is fast, it's because mass fights back. The closer you get to light speed, the more your own energy turns against you. Motion becomes resistance, and acceleration becomes impossible. E equals mc squared isn't just a formula, it's a warning. The faster you go, the heavier the price. Gravitational time dilation, how gravity bends time. You've heard the phrase, time flies when you're having fun. But in the universe, time doesn't just fly, it bends. And one of the things that bends it? Gravity. It sounds strange, almost mystical, that something pulling you down could also be pulling at time itself. But this isn't science fiction. It's Einstein's general relativity. And it tells us something mind-blowing. Gravity slows time. The stronger the gravity, the slower time moves. Picture 2 clocks. One sits on the surface of Earth. The other is on a mountaintop, a few thousand meters higher. That second clock? It ticks just a little bit faster. Not because it's broken, because it's farther from Earth's gravitational pull. This effect is called gravitational time dilation. And it means that time, something we think of as constant, actually flows differently depending on where you are in a gravitational field. The deeper you are in gravity's grip, the more time stretches, and the effect isn't just theoretical. In 2010, scientists put incredibly precise atomic clocks on airplanes and compared them to identical clocks on the ground. They tick differently. Today, your GPS uses satellites that orbit high above Earth, where gravity is weaker and time ticks slightly faster. If we didn't adjust for that, your location could be off by miles. But the real twist? This effect grows more intense the closer you get to something truly massive. A black hole, for example. Its gravity is so strong, it can nearly freeze time. Imagine watching someone fall toward a black hole. From your point of view, they slow down, slower and slower, until, right at the edge, they appear to stop, stuck in time. But from their point of view, they're falling freely, fast. No slowdown at all. Two realities. Both correct. Because in the warped fabric of space-time, gravity doesn't just pull. It curves the very passage of time. And here's the deepest idea of all. Gravity isn't really a force in the old-fashioned sense. According to Einstein, it's geometry. Mass bends space-time. And that bending tells objects how to move, and tells time how to flow. So the next time you drop something and it falls, remember, it's not just gravity pulling it down. It's space-time curving, guiding everything, and every tick of every clock, along the path of least resistance. And in this universe, your height, your motion, your position near a planet or a star, all of it affects how much time you get. Time isn't fixed, it's flexible, and sometimes it slows down in the dark.